This is a video dealing with solubility. There are two components in a solution. The solvent, which is present in greatest amount, it's the substance that does the dissolving, and there could be one or more solutes. These are present in lesser amounts. These are all other components that are dissolved in the mixture. So the solutes are dissolved. Aqueous solutions will be the solutions that we'll be dealing with in this unit. An aqueous solution is a solution with water as the solvent. There are two factors in the solution process. There is a natural tendency to mix, and we're going to take a look at that, and then an intermolecular forces component that we'll also take a look at. So let's take a look at that natural tendency to mix. There's a term that we need to become familiar with. It's called spontaneous. When a process happens on its own without outside assistance, we can say that process is spontaneous. It's determined by a combination of increasing entropy and decreasing energy. When the process releases energy, or when it's exothermic, that would tend to make it spontaneous. So it's a combination of these two regarding the particles, right? Increasing entropy of the particles and decreasing energy of the particles involved. Entropy is the extent of randomness in particle distribution, or the extent to which energy is distributed among the particles. So entropy typically will increase within the universe naturally. That's the second law of thermodynamics. The formation of solutions is favored by the increase in entropy that accompanies mixing. So when particles that are pure break apart from each other and mix together, there's a randomness that increases in that particle distribution, or we could say that the energy that's distributed among the particles can also be increased that way. So sometimes mixing is endothermic though. So what we see happening is that if the energy of the particles increases because it's an endothermic mixing, in other words, you mix the two substances and you touch it and it feels cold, or you put a thermometer in and the temperature goes down, the reason that's happening is because entropy is a larger factor in those mixing situations. So you can have endothermic or exothermic mixing processes. So let's take a look at intermolecular forces next. Intermolecular forces come in four types, and there are a few different other types out there, but four general types that we're going to take a look at. Dispersion forces are caused by the attraction of transient or temporary dipoles. Remember, a dipole is a delta plus or a delta minus charge on a molecule. And this happens when we have nonpolar molecules. Dipole-dipole interactions are caused by the attraction of permanent dipoles between polar molecules. And dipole-dipole interactions sometimes are eclipsed by dispersion forces if we see very large molecules. Even though they're polar molecules, the dispersion forces can play a bigger part. We'll take a look at that more later. Hydrogen bonds is another type of intermolecular force we're going to consider. These are very strong dipole-dipole interactions, so strong we put them in a category by themselves. And they occur between the hydrogen, which is going to be a delta plus on one molecule, and the small and highly electronegative nitrogen, oxygen, and fluorine that we would find on another molecule, and these would be the delta minuses. And because hydrogen has no other electrons, so when we sometimes take the electron away from it, there's only a bare proton. This happens uniquely with hydrogen and these very electronegative and very small atoms. So it's kind of a unique situation there, or a limited situation, very defined there. Ion dipole interactions are attractions between a positive or a negative ion and the oppositely charged dipole, in other words, the delta plus or the delta minus of an adjacent polar molecule. So for example, when sodium chloride dissolves in water, we see that the delta plus and delta minus charges on the water molecules pull on the positive and negative sodium and chloride ions respectively. All right, the effect of intermolecular forces on a solution is that there are really three types of intermolecular forces we need to pay attention to. Solute-solute interaction, In other words, when solute particles are attracting solute particles and holding that solute together, or solvent-solvent particles where the solvent particles are being held together by some intermolecular attraction. Now these must be overcome. You have to break apart the solute particles from each other and the solvent particles from each other for mixing to occur. And then also, solvent particles and solute particles have to be attracted to each other. And that solvent-solute attraction between the particles needs to be greater than or comparable to the other two interactions for mixing to occur. Now, it doesn't have to be greater than because of the effects that entropy can play on it, right? It's not just about the change in enthalpy that's happening when reactions occur. The fact that particles will naturally tend to become more random plays a part here, and sometimes the entropy has a bigger effect. Let's take a look at figure 13.3 in your textbook. And if we look at that right here, we're going to see that we have a sodium chloride ion. The sodium ions would be the purple models there, and the chlorine ions would be the green ones. And then water molecules are these white and red Mickey Mouse looking molecules here. So what happens is the crystal gets pulled apart or dissociated into ions. So we see that the water is pulling apart the sodium ions and the water is pulling apart the chloride ions. And what happens next is the water molecules surround the sodium ions, orienting their delta plus part, which is the hydrogen end, towards the negative chloride ion. And they also flip around and surround the sodium ions, where the negative oxygen and the delta negative oxygen end of the molecule is oriented towards the sodium ion. And they surround those molecules three-dimensionally. So the breaking apart of the crystal into individual ions is called dissociation. That's the first step in the dissolving process. And the surrounding of the ions by the solute particles is called solvation in general for any solvent. If the solvent's water, in other words, if it's an aqueous solution, then we call the solvation process hydration. Now this doesn't have to happen with only ions. In this case, we have ion-dipole interactions happening here in that mixture. This could happen if you have other intermolecular forces. For example, if you put some sugar molecules in water, the sugar molecules, table sugar molecules, would dissolve in the water, and there would be different intermolecular forces at play, but we'd see the same process. The crystal would be broken apart into particles. In the case of sugar, it would be broken apart into individual molecules of sugar, and then the molecules of sugar would be solvated by the water molecules, similar to what we see happening here. While we have the book open, let's go ahead and take a look at our next diagram in the book, which is a diagram that has to do with endothermic and exothermic processes. So we see if you break apart the solvent molecules into separated molecules, and you take the aggregated solute molecules, and you could say you disaggregate or break apart those, we get separated solute molecules. Breaking apart those solvent and solute particles from each other takes energy, so there's a positive delta H. In this case, on the left-hand side, we have an exothermic process. So when the solvent and solute particles mix, there's more energy release, more delta H negative than what we have positive there. So the overall decrease in enthalpy means that we have an exothermic solution. If we go through that same process, but the mixing of solute and solvent is less of a negative than it takes for these two positive processes, then what we see happening is an endothermic process. So there's an equation that we can take a look at here, where the overall delta H of the solution is equal to the delta H that it takes to break apart the solute and the delta H that it takes apart to break apart the solvent. And typically we'd have to put energy into those. That would be a positive delta H in both of those. And then you have to add on the delta H of the mixing, which would be a negative delta H. If you add all that up together, you can sometimes get an endothermic process. And remember that the reason it can be endothermic and still occur is because entropy always increases. There, the entropy takes over and causes that to happen. So sometimes you make a mixture and put a thermometer in it, or you feel it as it's mixing and you feel it getting warm. That's exothermic. And sometimes you feel it getting cold. The temperature goes down on the thermometer. That's endothermic. And both of those are possibilities. So let's take a look at saturated solutions and solubility next. Solubility is a way that we can describe how much stuff dissolves. So if you mix a solute with a solvent, you make a solution. But if you continue to put solute in there, sometimes what's going to happen is the solute won't mix anymore. We'll find that the solute just falls down to the bottom of the container. So if I take a beaker of some water and I add sodium chloride to it, if I keep adding sodium chloride, I'll eventually get to the point where the sodium chloride no longer mixes in. And what happens then is we get a dynamic equilibrium that occurs. So as we're mixing these two and the dissolving is happening, some crystallization is happening as well. If you were to put a really sensitive camera and do some slow motion photography, you would see that the crystals are constantly going into and coming out of solution as dissolving and crystallization is happening if you were to look at the crystals that were on the bottom of that beaker. So when that happens, when a solution reaches a balance point and it just keeps moving back and forth there, and you can imagine the water cycle on the Earth, where water is constantly leaving the surface of the Earth and going into the atmosphere and coming out of the atmosphere and going down into the surface. If the temperature stays constant, that balance is always in place, where we have water that's evaporating and water that's condensing. And that's a type of a dynamic equilibrium within the water cycle. Well, we can see the same thing happening here in this physical process. So a saturated solution is a solution that's at equilibrium with undissolved solute present. So in other words, the sodium chloride that's at the bottom of the beaker. And if you continue to add more solute, it won't dissolve. So this is the maximum amount of solute that is dissolved at a given temperature. Solubility, then, is the amount of solute needed to form a saturated solution in a given amount of solvent at a given temperature. And it is temperature dependent. If you warm up the solvent particles and they move a little faster and they separate a little bit more, you can dissolve more stuff if it's solid and liquid generally. A little bit less stuff if it's gas. We'll take a look at that in a little bit. Now, an unsaturated solution would be a solution with less than the maximum amount of solute dissolved, and a supersaturated solution can also occur. Typically, if you warm a solution up, dissolve a solid or liquid solute in it, you can get more solute to dissolve at a higher temperature, as long as it's solid or liquid. Then if you cool it down very gradually, you can sometimes get those solute particles to stay dissolved, even though we end up with more than the maximum of normal amount of solute dissolved at a lower temperature. And we call that a supersaturated solution. Supersaturated solutions are typically very unstable. If you drop a little crystal in there of the solute, we call that a seed crystal. Or if you agitate it, or sometimes if a little speck of dust falls in there and behaves as what's called a nucleation point, you can see that the solute will very quickly come out of solution and the solution will drop down to the saturation point at that lower temperature. So if we have more than the normal max dissolved, we call that a supersaturated solution. Let's take a look at some factors affecting solubility. So again, solubility is how much dissolves, and we can generally go with the statement like dissolves like. So solutes and solvents that exhibit similar intermolecular forces tend to be soluble. In other words, they tend to mix with each other. The stronger the solute-solvent interaction or attraction, the greater the solubility, the more that we see them mixing. So you don't need to know these exact values, but they are in fact defined with some numbers. Insoluble is when a very small amount of stuff or none dissolves. And typically we'll see less than 0.1 gram of solute dissolves in 100 grams of solvent. Now we have to specify how much solvent we have here to really quantify solubility, because of course if we had 1,000 or 10,000 grams of solvent, we could dissolve a different amount of solute in it. So we typically reference to 100 grams of solvent. If a substance is slightly soluble, then that means just a little bit dissolved. So like between 0.1 grams and 1 gram in 100 grams of solvent. And that would be 0.1 grams of solute or a gram of solute. And then we say it's soluble if more than 1 gram can dissolve in 100 grams of solvent. Now, if we're dissolving liquids, we have these different terms we sometimes see: miscible. So if you take a solute that's a liquid and a solvent that's liquid and you mix them together, we see that the pairs of liquids that mix in any proportion, like if you mix some isopropyl alcohol and water, for example, they can mix in any proportion. They're said to be miscible. And then also for liquids, we can use the term immiscible, which means the pairs of liquids that are insoluble in each other. There's a little bit of confusion around the term miscibility, and it's kind of used slightly differently by people in different professions or different areas. So I don't want to get too caught up into that and what that really means. I do want to take a look at hydrocarbons. These are carbon chains and their solubility. Hydrocarbons with only hydrogens attached to the carbons in the carbon chain exhibit dispersion forces, as they're just very much largely symmetrical and therefore nonpolar. But if an alcohol group, for example, and that's where you have an OH attached instead of a hydrogen, is attached to that chain, the molecules exhibit hydrogen bonds, because now we have a really small oxygen atom that could attract to the hydrogen atoms of a different molecule that was a hydrocarbon. And if you have multiple alcohol groups attached, they exhibit more hydrogen bonding. So hydrocarbons do not mix with water unless one or more alcohol group is on the carbon chain. So for example, if you have octane, C8H18, that typically is a big component in gasoline. We won't see that it's going to mix very well with water at all. In fact, we'd see that if you tried to mix it, it would just layer out into a gasoline layer and a water layer, and the gasoline would float on the water because it's less dense. But if you attach an alcohol group onto a carbon chain, we can all of a sudden get some hydrogen bonding that happens between the carbon chain and water molecules, and then it would dissolve in water. And other functional groups can exhibit hydrogen bonding as well. For example, if you have a ketone group where a carbon is attached with a double bond to an oxygen somewhere on the carbon chain, that can work the same as an alcohol. Let's take a look at table 13.2 in your textbook and see the effects of that. So on table 13.2, this is on page 521, we can see that methanol is infinitely soluble, so it's miscible, and these are that's a liquid. It's miscible in water, and then here's solubility in C6H14 is ethane. It's another type of a solvent we could have. Or, I'm sorry, hexane, another type of a solvent. So here we see a carbon attached to another carbon attached with an alcohol. This is ethanol. The OH is the alcohol group, infinitely soluble. And then propanol, infinitely soluble. But now, as we start to get more carbons in the chain, we see that the nonpolar end of this carbon chain is having a little bit of an effect. So it's not infinitely soluble. There is a solubility to it, a number that we can place on that. So 0.11 grams of solvent would dissolve in 100 grams of water. And then here we see if we have pentanol, where the carbon chain gets a little bit bigger, a little bit less dissolves. If we have hexanol, this is 6 carbons. Pentanol has 5 carbons. Hexanol has 6 carbons in the chain. We get even less solubility. So the longer the carbon chain, the more nonpolar effects we see and the less soluble we see in water. And again, if you had what's called a glycol, which is a carbon chain with 2 alcohol groups attached, we'd see even greater solubility than we see with methanol, for example. All right, so then there are some factors that can affect solubility. So one of the factors affecting solubility is pressure. Solids or liquid solutes are not really affected by pressure, but pressure does affect the solubility of gaseous solutes. And it turns out that gaseous solutes solubility increases, so we get more stuff dissolved if it's gaseous solute as the partial pressure of the gas increases over the liquid. And this is described by Henry's law. So Henry's law, as described here, has a Henry's law constant. And in our sample exercise 13.2, they give an example of using Henry's law. Now, Henry's law is actually dependent on a few different factors, or I'm sorry, the constant value used in Henry's law is dependent on a few different factors. So it's proportional to the substance that's being used as the solute and the solvent and the temperature. So it changes for every substance. But we can see that the Henry's law constant is given right in the problem. I'm going to let you guys take a look at this in a little bit more detail on your own. But the Henry's law constant for carbon dioxide and water at the temperature given in this problem is 3.4 times 10 to the negative 2. So this is for CO2, and this is in sample exercise 13.2. This Henry's law constant is going to vary for every different substance. So the solubility of a gas in a liquid, S, and G for, the solubility of gas in a liquid solvent, S for solubility, G for the gaseous solute, is usually expressed in units of moles per liter. The Henry's law constant value is the K value, and notice that in this sample for CO2, it's expressed in moles per liter atmospheres. And then the partial pressure of the gas above the liquid in the solution, and of course we'd have to have units here of atmospheres, right? So you can use Henry's law when you're dealing with pressure, and that is something we really only pay attention to with gases. And then finally, we can have other factors that can affect solubility, specifically temperature. And again, we're talking about within an aqueous solution. So for most solids and liquids, we see that solubility increases as temperature increases. And we can see that on figure 1318 in your textbook. These are saturation points that are graphed out for all different substances. We have solubility on the y-axis, temperature in degrees Celsius on the x-axis. We can see that for most solids and liquids, we see an increase in solubility. And there are some things, solid and liquid solutes, where they actually decrease solubility as temperature increases, but those are kind of outliers. We don't see very many of those. And then for gases, solubility decreases as temperature increases. So if we take a look at gases on this figure 1319 in your text, you can see that they trend downwards, solubility on the y-axis, temperature on the x-axis. As temperature goes up, we see decreasing solubility. So if you're going to try to fish and catch the big lunkers that need a lot of oxygen, where the big fish are, is going to be down in the deep water where it's very cold and there's a lot of oxygen dissolved. If the water gets warm, less oxygen gets dissolved, and that means that affects the aquatic life, and typically you won't find the big fish in the warmer water. This should help you with the first problem set, problems 13 through 37 in chapter 13. As always, if you have any questions, make sure you get in touch. Good luck.